erosion assessment, and big pleasure and thanks, Michael, a lot that you agreed to participate and give a lecture in this third course of Megapolis covered by EHS and WASWAC communities. So, Michael, floor is yours. Very welcome, and yeah.
Okay, so hopefully everybody understand me. So the microphone should be on. Okay, thank you very much, Sergey, for inviting me to your workshop here this afternoon, and also good afternoon to the audience. And maybe I directly share my screen. So give me a second. So is that working now? Hopefully.
Yes, we can see your screen. So please.
Okay, so it's also the presentation mode, I hope, right?
Yes, everything is fine.
Okay, perfect. So yes, today I would like to give you, let's say, a talk about integrated soil erosion assessment. I would like to focus a little bit on different concepts that are on the market and methods and applications that have been, let's say, applied in the last decades, let's say. Maybe I introduce myself a little bit. I am working in Pavia University. So if my screen is getting along, so Department of Earth and Environmental Sciences of University of Pavia in Italy. So that is one of the oldest, second oldest, I guess, university in Italy, founded in 1361. So for those of you who don't know where Pavia is, so it is in northern Italy. So we are in Lombardy region. And actually, it's the southernmost part of Lombardy region, so the Pavia province. And we are roughly 30 kilometers south of Milan. So that is, let's say, in the middle of the Po plain, actually. So, and Pavia is on the Ticino River, close to the confluence with the Po River. And the area is famous for the paddy rice agriculture, as you see here in the images. And since the Pavia province is also covering the northern parts of the Apennines, we have also one of the largest white wine growing areas in Italy. And part of the paddy rice, as you see around Pavia, you have all these water surfaces. Pavia is also famous for mosquitoes in the summer months. So if you want to visit, it's better in the winter months, actually. So, and then since November, 1st of November this year, I'm also working at SALF. So it's the Leibniz Center for Agricultural Landscape Research in northeastern Germany. And there I'm leading the working group on soil erosion and feedbacks. And as you see, so the area seems to be quite flat. However, as you see here from the photos, so we are in a hummocky ground moraine landscape mainly. However, also over here, we have some soil erosion by different agents, so by wind and by water mainly. And there are also others, as we will see in a moment. So coming back to the topic after the introduction of myself. First of all, I would like to focus a little bit on the different erosion processes that we do have with a focus on Europe. And then I would like to stick especially to the soil erosion processes by water, actually. So, first question, why should we deal with soil erosion? So why is that important? Soil erosion is destroying soils. And soils, as you see over here, is the basis for our life and the most important production resource. 95% of our food is produced on soils. And then the soils play also a very important role in the ecosystem and ecosystem functioning. So soils store water, for example. Soils provide nutrients, plants with nutrients. And soils give also stability, for example, to plants. And then soils are also very important to biodiversity. So it's quite astonishing that actually 2/3 of the species we have on Earth are living under the soil surface. And just in a handful of soil, we have roughly 100 million bacteria, 100,000 protozoa, and 10,000 nematodes, for example. And we have just in a handful of soil 50 kilometers of microbial networks. So quite rich and quite important, the soil also for the biodiversity. And last but not least, there's also the link to the climate, because the soil is the third largest carbon stock on Earth, and soil erosion may lead to the release of carbon to the atmosphere on the one hand. On the other hand, soils can store CO2 in the soil, or carbon in the soil in the end. So that has repercussions, obviously, also on the climate. So the big problem is that the soils are degraded and lost by, for example, different soil erosion processes, as you see here also in the image that is from Southern Africa, KwaZulu-Natal, an image of an area where I did long time ago my PhD thesis. Okay, so soil erosion is especially let's say dangerous if it is let's say affecting agricultural areas, and on Earth, let's say agricultural areas cover 38% roughly of the Earth's ice-free land, and as Frawley stated, especially accelerated water erosion is one of the major socioeconomic and environmental threats because of the on-site and off-site damages related to soil erosion. But we will stick to that a little bit later on. The images over here are from Sicily, Madonia area, where you see that we have, for example, on the left-hand side, gully head completely destroying the fertile soils you have over there, thick, dark topsoil layers, which are very fertile. On the right-hand side, you see there is also some earth flows, some mass movements that are affecting the agricultural areas here in the northern parts of Sicily. Okay, so sticking a little bit to, let's say, the European perspective, the soil loss is, let's say, related to different media, so water or wind, as you see over here in the images. Anyway, the soil erosion by water in large parts of Europe is much higher than the other types of soil erosion. So you see that's the scale here for the water erosion is getting up to 50 tons per hectare and year. And if you have a look at the image, especially the Mediterranean areas are affected by these soil erosion processes, whereas in the northern parts of Europe, let's say northern Germany, Poland, the Baltic states, as well as Sweden and Finland, there are just, let's say, very low values of soil erosion by water. If you have a look on the right-hand side, soil loss by wind, you see that the total losses are much smaller. So we get up to 3 tons per hectare and year over here. And the areas mainly affected are the coastal areas, as you see here, Denmark, the eastern parts of Great Britain, southeastern parts of Great Britain. And we have also Romania here, Danube area, which is affected by wind erosion, but also here the Po Plain, southeastern Italy, for example, and the central parts here of Spain that are affected by wind erosion. Anyway, a part of soil erosion by water and by wind. There is also another type of soil erosion that should be not neglected, especially in the agricultural areas. So where we only have this type of soil erosion, that is tillage erosion. And here you see that, especially here in Northern Europe, in the Po Plain, the flat areas, especially where we have agricultural, intensive agriculture, there we have quite high erosion rates by tillage, as you see here also in the on the right hand side. So if we till every year, so there is a net, let's say, transport of soil, and the landscape is changed accordingly. So then we have a fourth type of soil erosion, which is due to harvesting. Soil loss by crop harvesting, as LCH. So as you see over here, the values are again a little bit smaller than for tillage erosion. However, that is also one, let's say, type of soil erosion that is completely neglected, is a kind of erosion that is mainly related to crops that grow under the soil surface, like potatoes, or that have roots in the soil, like sugar beets. And as you see here on the left-hand side, so we have mainly in the northern parts of France, where we have the sugar beets, Belgium, the Netherlands, parts of Germany, Poland, and Denmark, where we have the highest values of soil loss by crop harvesting. The two crops mainly here, let's say, delivering sediments, or where we have soil erosion, are sugar beets and the potatoes, as you see in the image on the left-hand side. Anyway, what we have is we have different erosion types, so water, wind, tillage erosion, and crop harvest erosion. And here on the right-hand side, you see an image where the number of different erosion types is listed. So in yellow, we have just one type of erosion, and in the dark brown, number 4, we have then the combination of 4 different types of soil erosion. So that means we might have dominances by specific erosion types, but in the end, these soil erosion processes might also interact. These are some topics that are, let's say, still not really studied yet. Yeah, if you have a look on the national scale, here on the right-hand side, you see these diagrams where you see in blue the water erosion, in yellow wind erosion, and in red we have tillage erosion, and in green is the soil loss due to crop harvesting. And you see that mainly water erosion is dominating, especially here in the southern parts of Europe, but also in the central parts of Europe. However, also tillage erosion plays a very important role. There are the red bars here. So you see that should be not neglected. As I said before, this analysis that we have done in the past are, let's say, mainly related to the agricultural areas, obviously. Good. So, and if you put it then on the NUT3 level for EU, so the regional level, so you have certain dominances, and the blue areas are the areas where we have water erosion dominant, and in red, the areas where we have the tillage erosion. However, it seems that tillage erosion plays also very important role. However, it is not really studied like water erosion. So almost the last decades where people are studying then in the end tillage erosion. And in yellow, the areas around the coast where we have dominance of wind erosion. Anyway. So a part of the dominances, as I have said before, there is also the, let's say, concurrence of the different erosion processes. In this case, we have in the agricultural area 4 different types of soil erosion. And we should take that keep that in mind, that sometimes not only soil erosion by water is, let's say, degrading our soils, but there are also other types of soil erosion. Good. And actually, that's where I want to focus on, soil erosion by water. And this is here an old image from the late 90s, actually. So here we are still in Southern Africa, KwaZulu-Natal, and we have over here an area that is completely eroded. Actually, the topsoil is completely gone, and one of the reasons for that you see also here in the background. So that was an area that was completely overgrazed. So we had too much cattle here on the fields. So compacting the soil. In compacting the soil, we have a decrease in infiltration. If you have a decrease in infiltration, we have an increase in surface runoff. And according to the increased surface runoff, we have then also, let's say, an increase in surface erosion by laminar or turbulent flows. So there is also, if we deal with soil erosion, the monetary dimension of soil erosion processes. And as Pimentel already in 2006 stated, we have, due to erosion processes, a loss of 10 million hectares of cropland actually each year. So that is quite a lot. And as you know, once the soil is lost, it is difficult to, let's say, generate a new soil. So pathogenesis is quite slow. So you can erode the soil within one event, maybe one extreme event, lasting maybe one day or even a couple of days. But the soil formation takes hundreds or thousands of years, actually. So that is a pity, because once the soil is gone, so then also the agricultural potential is decreasing, or actually it is completely reduced. So if we have a look at the damages that are created by soil erosion, by offsite and onsite damages, there was a calculation by Bloom, Secretary General of International Soil Science. They came up with 450 billion euros per year globally in 2001 as a monetary dimension of, let's say, soil erosion and the related offsite and onsite damages. EU-wide, there was estimate by Panagos in 2015. They came up with 20 billion euros. And if you divide these, let's say, globally estimate of 450 billion euros per year worldwide, you come up roughly, it's a little bit less since we are 8 billion now, 60 euros roughly per year per person. So you can say, okay, 60 euro is not that much, so we should care about it. Anyway, the problem is that soil erosion is not distributed equally on our globe. So, and as you see here, we have the water erosion vulnerability map. The soil erosion process is the most intensive one. And if you have a look, you see the red areas that are distributed not equally around the globe, but we have some areas where we have some concentration of these soil erosion processes, especially here around the Mediterranean. We have the Sahel zone, Southern Africa, Madagascar, the northern parts of Australia, southeastern parts of Australia, New Zealand. So we have the eastern parts of Asia. And then if you're going here to North and South America, so southern Chile, southern parts of South America, along the Andes, and especially also here in Northern America, US, Great Plains, for example, and Rocky Mountains and Appalachians, where we have the concentration of soil erosion processes. So that means these processes are not distributed, let's say, by case, but there are specific drivers behind. And if you have a look here on the distribution, already a couple of drivers might come to your mind. So one is the climate. Soil erosion processes are very effective where we have intensive rainfall, and then also maybe periods of prolonged droughts, so semi-arid areas, Mediterranean areas, for example. Then we have areas like here in China, where we have very erodible substrates, like the loess, for example. And we have all the mountain areas where we have quite steep slopes, where also, let's say, the risk for soil erosion is quite high. So that means even if we have an average of 60 euros per person, the amount of soil erosion and the respective, let's say, monetary dimension is in some parts of the world much higher, and the population is suffering about soil erosion. The values are much higher than the average in the end. Okay, good. So coming a little bit to our research topics. So what are major research questions related to, in this case, the soil erosion processes by water? So first question is, what are these processes? So which processes are related to water erosion? And I will give a quick overview a little bit later. Then very important is what scales does these processes do have. In respect of time as well as of space, so the spatial temporal scales of these processes. And also one question that is up to now almost completely neglected, how do these processes interact? Yeah, so how do they affect each other? So, and here we are just talking about the water erosion processes, but in the end you have seen that there are also other processes by other drivers that are also affecting, let's say, these water erosion processes maybe. So then the question is, what concepts do we have to assess soil erosion in a qualitative or quantitative way? So means, so what are the models we are using in terms of getting some numbers, absolute numbers, or also some relative numbers with qualitative models? So, and then, so one thing I'm pretty interested in is the integration of different erosion processes on catchment scale. So what are these processes? So starting with the most spectacular big gully erosion, here we have an image from Southern Africa, KwaZulu-Natal again. Deep linear erosion processes that can be up to 20-30 meters of depth and respective widths, as you see here in the image. Then we have other processes that are let's say also linked on the water, especially on the water content in the soil, that is then in the end responsible together with the slope in, let's say, moving the soil along the slope due to gravity. Shallow landslides I also put in here, even though, let's say, if we are very restrictive, normally they are excluded from soil erosion by water. But anyway, soil water content plays an important role in this process, so I normally put it also in. Then we have the processes that are called interrill erosion processes. Here an image from an agricultural area in the Mugello Valley, northern parts of Tuscany in Italy. So you see that the rills are developing, especially along the tracks of the tractors, so where they go along with their tires, compacting the soil. Compacting the soil means that we have decrease in infiltration, increase in surface runoff, and then the flow is accumulating and eroding, especially where it's getting turbulent, and maybe we have also some areas where we have some deposition here in the on the bottom. So then there are also some very interesting features like the badlands, where we have a combination of different soil erosion processes. In this case, we have this is an image from the northern Apennines, close to Pavia. So there we have rill erosion, interrill erosion. We have gullying, initial states of gullying. We have also shallow mass movements along the slopes over here. And in this case, the substrate is, let's say, very important. So we are here in the Pleistocene clays, and these badlands you'll find along the entire peninsula of Italy. So especially in the areas where we have these Pleistocene clay deposits. So, and then we have also small-scale processes that are also shifting sediments, let's say, further downhill, especially if you are on the slopes. So the impact of raindrops, splash erosion, and if you are, let's say, in a horizontal plane, then the sediments are just redistributed. But if you are on the slope, then we have a net transport towards the bottom of the slope. So, and then there are other processes like this one over here, piping, tunnel erosion due to subsurface flow. This is mainly related to specific soils that have high conductivities or a specific chemistry. Solonetzic soils, for example, they are very prone to piping. This is an image from Southern Africa, so where I worked in Swaziland, for example. Good, and then we have obviously also erosion processes by water, but in the drainage system itself, so bank erosion that is also contributing to the sediment discharge from catchments, as you see in this image. Okay, so in the end, these sediments are produced on the slopes by different erosion processes, transported then by surface runoff that can be laminar or turbulent. And then we have the concentration of the flows and the transported sediments at the lower parts of the slopes, where part of the sediments may be redeposited, but a large part also maybe enters the drainage system. So that is a function of the connectivity of the slopes to the drainage system. And in this case here, we are in the northern Apennines, where we have done an excursion a couple of years ago. And I hope that is working now. So there we had precipitation of just 25 millimeters in 2 hours, 25 millimeters of rain in just 2 hours in a very small tributary. So having, let's say, very small catchment area, but as you see over here, there's a lot of water coming down, but not only water, but also a lot of sediments, as you see here from the brownish color. Anyway. Okay, so as I said before, if we want to deal with different soil erosion processes by water, the scale of these processes is very important. So the temporal scale you find on the horizontal axis, and we have also the spatial scale that you find on the vertical axis. So, and here you are have listed the different soil erosion processes, starting with splash with the smallest scales in terms of time and space. So here we have, let's say, time scale of some minutes and transport of material from centimeter to decimeter scale. Then we have interrill erosion, where we are getting already a little bit longer spatial scales, rill erosion. We are already on slope scale, and then we have the gully erosion. That is something in between, let's say, slope and drainage system. So here the scales are even longer than 1 kilometer, and in the end we are then getting into the fluvial systems, So where we have then spatial scales that are bigger than also 100 kilometer up to thousands of kilometers. Same for the time. So we are getting from 1 minute in splash erosion up to years, months and years for gully erosion and the formation then of fluvial systems. So if we want to deal with these different erosion processes, we have to keep in mind that they are, let's say, dominant on different scales. So, and that makes it also a little bit tricky because so if you want to assess these processes, you have to get data that respect the different scales the process are acting on. So if you have a look at the different modeling concepts for soil erosion, as we have seen, we have to in some way reflect the spatial scale, but on the other hand also the time scale, and therefore we have then normally different models. So a spatial scale, we are starting from plot or field models, slope models, and then we have catchment-based models, for example, which have the biggest spatial scale. And concerning the time scale, we get from event-based models, short events, a couple of minutes, up to yearly average models, for example. Anyway, all these models use different modeling units that can be distributed or aggregated. However, these modeling units should reflect always the different scales the models are acting on. So, and that makes it in the end quite difficult. So, if we are talking about model approaches itself, so we have different ways how to assess soil erosion processes, starting with empiric black box models, like let's say some user-Lie approaches. So in the end, it's an empiric equation. So it's a black box approach. So we get something in and we get something out, but we don't really know what is happening in between. So conceptual gray box models, they are a little bit further. So there you know already a little bit about the processes that are acting. And then we have the physically based process-oriented so-called white box approaches, where you exactly know what processes are going on, and you also know how to describe these processes. So actually we are increasing the degree of causality getting from empiric models to physically based oriented white box approaches, but and that makes it difficult. If you increase the degree of causality, you normally increase also the degree of complexity, or in other terms, the parameter request, so the input data you need to drive these models. So that is often a dilemma, because on the one hand side, you know most of these processes and you can describe most of these processes with mathematical equations, but you don't have the data to drive these models. So in the end, you are interpolating or trying to downsize your data in order to get to higher spatial or temporal scales, for example. But in the end, we have some limitations, or often limitations, due to our data that we have available to drive these models. So, what are then the challenges of soil erosion modeling? Models normally reflect just one process. So that is a fact. And since they are reflecting only one process, normally they are scale dependent, as we have discussed before. So if you want to model splash erosion, you need other data, for example, as if you want to model gully erosion, for example. So then we have, let's say, a lot of models that are focusing on laminar soil erosion processes, so sheet or real inter-real erosion processes. And that was also, let's say, getting out by a study done by Borelli et al. In 2020, where they had to look at the different, let's say, publication regarding soil erosion modeling and which models they applied. And as you see over here in the light blue, that is the revised universal soil loss equation. So it's, as I said before, an empiric model, very simple. So data input is very, let's say, scarce. You can apply the usual or revised universal soil loss equation easily with data you get from the internet, for example. So that's why this model is also quite distributed on the globe, and that's why most of the studies use the usually as the assessment model to have a look at the soil erosion processes. So that means the focus is on sheet erosion, real interreal erosion, but as we have seen, that's only one process active on our slopes, but there are a lot of others. And some of the other models you have over here, for example, SWOT or LISM, they are using also parts of the user-Lee or parameters that are also used in the user-Lee. So SWOT, for example, is using or producing the surface runoff. So the R factor is not used, but the other factors are also imported in the SWOT. So in some way, it's also related to the universal soil loss equation, and that means it is or has an empiric component in the modeling procedure. Okay, so we said that we have mainly models that are addressing single processes, mainly focusing on laminar erosion. And what is also quite, let's say, difficult due to these, let's say, facts is that we have integrated modeling that is very complex due to different things. So we have first of all, different erosion processes, not only one, but different erosion soil erosion processes. We have different parameter requests because our processes are scale dependent. Scale dependent means spatial as well as temporal scale dependent. They have a specific spatial temporal distribution, and these processes might be also in some way connected to each other. So these are all challenges that are coming along if you want to integrate different soil erosion processes. So the big question is then, how can we assess and quantitatively simulate different soil erosion processes? So which concepts we do have available in order to get an answer to this research question. So one solution I would like to present you. So it's the so-called erosion response units concept that was developed during my PhD thesis with the group from Jena, Wolfgang Flügel. He was introducing the response units concept in hydrology, and I just let's say attributed it then also to soil erosion processes. So it is a distributed and process-based modeling entities concept. So, and the erosion response units, they can be defined as heterogeneously structured terrain units. They have a homogeneous erosion process dynamics that are controlled by the physiographic properties and the management of the human environment. So, due to these, let's say, properties, they allow also for a spatial scale transfer. And the nice thing is that you can derive these erosion response units by stochastic modeling. So if you have the knowledge about the distribution of existing erosion processes, you can use that knowledge in order to have a look at where else you have a potential for specific erosion processes. Okay, so I would like to show you then also how to extrapolate this information, so to get from, let's say, a test area towards, let's say, an entire big catchment. And therefore, I will show you a case study that we have done a couple of years ago. That was done by a PhD student of mine, Silvia Angelieri, from Sicily, from Palermo University, where we studied the San Giorgio catchment. This is a small area here within the Imera river catchment, and a little bit strange, the Imera catchment is draining towards the south. That's the Imera Meridionale river basin. As you see here in the map, it's draining towards the south of the Mediterranean Sea. And then we have the Imera Settentrionale, which is draining towards the north, towards the Palermo area over here. So obviously there's a watershed, as you see over here, where these two rivers are divided. However, they have the same name, so it's a little bit strange. But and the area where we worked on is exactly at the watershed divide, or located on the watershed divide between the two Imera catchments. And here in red, we have the so-called San Giorgio catchment. And the, let's say, task was to have a look at which are the processes active in the entire area. And therefore, we mapped, let's say, the processes here in the small San Giorgio catchment, and then developed our stochastic model that was then, let's say, regionalized to the entire catchment area here of the two Imera sections you see here in the image. Okay, so what are the processes active over here? So we had some rill inter-rill erosion, ephemeral gullies, so that are vanishing if you plow, but there are also deeper gullies that are difficult to eliminate by plowing. So these are the so-called permanent gullies. You have also some bank erosion along the small creeks or tributaries in the catchment. And over here you see also some gully acts. So also active over here in this catchment, due to the fact that we have quite high clay contents, are shallow landslides. And here on the steeper slopes, you have also some mud flows, as you see on the image here on the lower right. So actually, as I said, for the San Giorgio catchment, we mapped these different processes, as you see in the image. So we have in blue, bank erosion. In magenta, we have gully erosion features. Then the red polygons are mass wasting, and the brownish polygons we have then sheet and rill erosion. So you see also, let's say, the areas that are affected by these different types of erosion. And as you see, so there's a quite big area that is affected by mass wasting, shallow landslides, but we have also, let's say, large areas that are affected by rill inter-rill erosion, so aerial erosion processes here in the brown color. Good. So how do we get then, or how we develop then the stochastic model? So we have our target variable. In this case, the target variable are the different classes of soil erosion I showed here before. So, and on the other hand, we have spatially distributed predictor variables, for example, digital elevation model reflecting the topography, and we derived, I guess it was 25 different topographic indices, primary indices like slope, curvatures, the aspect, and also composed topographic indices like stream power index, topographic wetness index, or LS factor. We put also some climate information in, always derived by the terrain model. So, for example, insolation pattern can be derived also from the digital elevation model. So we have a vegetation map, land use map used that has aerial distribution, so covering our entire area. And we had also some spectral information that was inserted. So all these are continuous spatial information, whereas our soil erosion processes were converted into a point shape, and the point shape has obviously X, Y, and Z coordinates. Anyway, so using the target variables and the predictor variables, in the end we applied in some data mining. So in this case we used the TreeNet random forest approach. And in the end the model is able to explain the target variable by combinations of the environmental features, and that you can use then in the end this information to do the spatial prediction. The model is then used to predict, let's say, the probability of the occurrence of a specific soil erosion process. So that means combinations of different predictor variables that are typical for a specific soil erosion process. They allow you then to have a look at where else in my catchment I have the same combinations, and the hypothesis is where you have the same combinations of predictor variables, the potential to have a certain erosion process is then pretty high. Okay, so here is the procedure. So we have our response variable or target variable with the mapping of the different erosion processes that they were then, let's say, converted into point shapes. We have our topographic information, digital elevation model with the different topographic indices. And other environmental information like land use or geology or the spectral information that we included. And using TreeNet, which is a kind of random forest classification regression tree approach, we created then these erosion response units classification. So in the end, the susceptibility for having a certain process, soil erosion process in a certain place in our catchment. And this information that we developed here, the model we developed here for the San Giorgio catchment, and regionalized this information then in the end for the entire catchment, coming up with this ERU map or soil erosion susceptibility map, as we named it over here. Okay, so anyway, these stochastic models allow you also to get a little bit more into and explain why you have certain processes in a specific area. And here we have, for example, the variable importance. So which of the variables that have been used to create this model is then an important variable. So which variable is triggering the distribution of the erosion process. And here you see, let's say in black, we have the parameters that are triggering gully erosion, and in gray, we have those that are triggering rill inter-rill erosion. And you see, for example, for gully erosion, the SPI is the one that has the highest impact. So it's explaining best, let's say, the spatial distribution of gullies. SPI is the so-called stream power index, which is a combination of slope and catchment area. So where the slope is very steep and you have a large catchment area, so a lot of water that's accumulated, the probability to have gully erosion is quite high. So that is also quite logic. For rill inter-rill erosion, for example, is the elevation. We will have a look later on, so that is also explainable. And we have other variables like the aspect that are important for the formation of rill inter-rill erosion. So this variable importance helps you to interpret a little bit your modeling and to have a look at if it is plausible or not. So anyway, you can dig into a little bit further. So you can derive these partial dependence plots or response curves for the single parameters. And here we have, let's say, for the real interreal erosion processes, we have the partial dependence plots for elevation, aspect, and landform. And you see so elevation seems to respond here between 850 and 950 meters, especially to real interreal erosion processes. Whereas, let's say, the aspect is northwest or negatively east or southeast. So these are the directions where you normally get the rain from. And in terms of landform, so the upland areas corresponding here to the elevation are those who are having the highest impact and explaining best the distribution of our model. So upland and elevation is always, so in this case, a little bit tricky, but actually in this area over here, we have a specific geology that is outcropping, that is producing silty, fine sand texture of soils. So that is, let's say, the area where you have also very high erodibility, and that means in this case, then high disposal for the real interreal erosion process. So that means with these models, stochastic models, you can also dig into a little bit further into, let's say, the reasons for the spatial distribution of different erosion processes. Okay, so then we have in the end this regionalized map of the erosion response units. So we know where in our landscape we have what kind of erosion process, or where the potential for having this process or susceptibility to having this process is very high. Okay, so that leads us then to the next step, because if you know where in your catchment you have what kind of erosion processes, you can apply then specific models in these areas. So you don't have to apply the models for the entire area, but you can specifically apply the models just in the areas you are identifying here for specific erosion types. So, and that concept, let's say, was applied also in different studies. So you have, on the one hand side, you have the spatial distribution of the erosion potentials, so the erosion response units. And according to the process that is, let's say, dominating the spatial unit, you can then apply different, let's say, models. So for real interreal erosion, you can apply then maybe the USLE or unit stream power erosion deposition model from Mitasova. You have, for example, linear gullies. So you can apply some gully model. So, for example, the Sidorchuk models, Dimgol, Stapkul, for the different gully evolution stages. Or you might have then also some mass movement translational landslides. Therefore, you could apply then some landslide model. So all these models produce an amount of sediments in the area where they are applied. And in the end, let's say the sediments that are available for transport, they have to be, let's say, connected then to the river network and transported to the river network using some transport, sediment transport routine, for example. And if necessary, maybe also you have some deposition, so you can apply then also some depositional module. So in the end, if you apply this approach on catchment scale, you are able then to get then the integrated catchment response in terms of the sediment yield of your catchment that is, let's say, reflecting then the different erosion processes. Okay, so the second case study is, let's say, was done start of the years 2000 in Swaziland in Southern Africa. So we are, let's say, eastern part of, let's say, the capital of Swaziland, Mbabane. in the so-called Motoma area, which is an area which is affected very intensively by gully erosion processes. So we have very large gullies, so they developed within even short time periods, a couple of years. So during 3 or 4 big precipitation events that are related to some hurricanes coming in from the coastal areas. And as you see, so here these gullies are quite deep, so up to 15-20 meters depth, and they are having also already eroded quite a wide area. So as you see over here, producing a lot of sediments that are washed into the river network, as you see then here on the lower parts of the image. On the other hand, we have then these inter-rill erosion processes with rills that are already getting into some deeper permanent gullies, as you see here in this image. So these are the two processes that are mainly acting, so sheet erosion, rill inter-rill erosion, and gully erosion processes. And we use then the ERUs, so we delineated also for this area, so we knew where we have what kind of erosion process, and we applied then, let's say, for the inter-rill erosion, the usually on the one hand side, and for the gully areas on the other hand, we applied, let's say, the gully models based on the work of Alexei Sidorchuk. And you might know, so gully erosion has different evolution stages. So we have a first initial and very dynamic phase where most of the morphometric parameters of the gully is developed. And we have a static phase that is covering 95% of gully evolution. So, and actually there are two models that can in some way simulate these two evolution stages. In the end, you get out soil erosion per response unit area, and then let's say we applied also a sediment routing routine in order to get then the integrated catchment response. So in our case, there was then also the question, you have active gullies and you have passive gullies. So active gullies, they are still delivering a lot of sediments, and the passive gullies that are the stable ones that are compared to, let's say, rill inter-rill erosion process. So not that much sediments that are coming from these passive gullies. The question was, how can we differentiate between active and passive gully systems? Because our ERU map is showing us just where we have gully erosion potential, but not if it is active or not. And therefore, we used then a simple approach using multispectral data in order to calculate the transformed soil-adjusted vegetation index. Normally, you don't have vegetation at the active gullies. If you combine then the information of the ERU, where you have gully, and the information if you have vegetation or not, you can differentiate then also between active and passive gullies. For us, it is important to have a look at where the active gullies are, because that are the areas where most of the sediments are coming from. And in the end, here, for example, for our Lambagnoni area in Swaziland, we have then also differentiated the different areas where we have active gullies. Here, these are the black dots you see in the lower right image. Good. So then, in the end, we were able to calculate the soil erosion per pixel or per ERU, as you like. And we applied then a simple sediment routing routine in order to produce then the entire sediment discharge of the catchment. So that is then integrating rill, inter-rill erosion and gully erosion. And let's say in our case, the total sediment yield, including gully erosion, was up to 20 tons per hectare in the year. And the gullies contributed up to 30% of these 20 tons per hectare in the year. So that's quite a lot. And as I said before, as we have seen by the publication of Borelli, a lot of applications are just focusing on rill inter-rill erosion processes, and the others are neglected. But as you see over here, for example, gully erosion is quite important and should be included, especially if you have active gullies. Good. So, and the thing is, gully areas are just less than 1% of the catchment area, so they're very effective sediment sources. Okay, so what are then after these case studies, having a look at how to derive these ERUs and how to apply it, and also in modeling. So what are the research deficits and future perspectives I do see, let's say, in soil erosion modeling at the moment? So first of all, it's the integration. So we have to get further with the integration of different soil erosion processes on catchment scale, integrating different models, for example. And let's say the response units concept is one concept that might help for doing this integration. But for sure can be further developed, especially also in terms of the time scales that are covered. So then what we should incorporate are also connectivity approaches to have a look at how much of the sediments produced along the slopes are in the end then also getting into the river network. Also one question that is very important is how different processes do interact. So that is also one thing that is very important and not studied really in the past. So one further topic is, let's say, connected to the derivation of input data for these soil erosion models. So especially concerning the soil characteristics and precipitation. So there we need, or often we have just point information, single soil profiles, or single precipitation stations. But in the end, we need the information, let's say, on a continuous spatial scale. So therefore we need specific regionalization methods. Stochastic approaches are quite sophisticated to do that job. So digital soil mapping, for example, is also widely using these stochastic approaches. And then in the end, my perspective, so real-time modeling would be nice to do in future with all these new satellite data, high resolution information. So in the end, one can come up also with some nice early warning systems. So actually, most important question is which factors are influencing these water erosion driven processes and what kind of data we do need really. That are the factors you already know: climate, vegetation, soils, terrain management, and topography, the main factors influencing soil erosion. And let's say, if you have a look at the data quality and availability, it looks a little bit different for the different factors. Climate and precipitation, we do have information, but often point information, but here the problem is the spatial distribution of this data. Vegetation now is quite okay because we have information from satellite data we can use in order to create vegetation or land use maps. For example, Sentinel already on 10 meter scale can be used. Soils are very difficult because it's 3D medium, so it's not only what you see on the surface, but it's also the stuff below our feet that is important. So, and that is very difficult in order to get there, let's say, spatial information. So especially if you are in heterogeneous environments. So terrain management also quite okay. So you can get also from remote sensing data nowadays, and topography. There is also the question about the spatial resolution of this data. But let's say in terms of digital elevation models, we are normally we are quite well, doing quite well, because we can use also, let's say, high resolution LiDAR data or drone data that are doing a quite good job. So let's say the factor that is less represented normally in the models, in terms of quality and quantity is, let's say, information about the soils. And it's not only the soil type, but it's also the soil properties that we need for a proper soil erosion assessment. So first of all, the texture, skeleton, and the characteristics of the soil in terms of infiltration, hydraulic conductivity, that is related to soil density, porosity, root network that you have, the soil organic content, soil structure, and soil depth, for example. So, and often you just have, let's say, information about soil type. Maybe if you have a soil map, you are already lucky in large areas around the world. So the problem is that you have always, let's say, point type data, but in the end, all these analysis that we're doing on a soil profile or at a specific point, in some way we have to get into space. And therefore, let's say you can use then also new techniques like proximal sensing, remote sensing, for example, as you see here in these images, where we did, let's say, integration of different information, soil profiles, plus proximal sensing of the underground, for example, and remote sensing, hyperspectral remote sensing in this case, in order to get, let's say, spatial distributed soil information, spatially distributed soil map, as we did then here in this area. Good. So the question is always how to get from the point to the spatial distributed information that you need normally to do, let's say, catchment assessment in terms of soil erosion processes. So, and the procedures you normally use, so for example, digital soil mapping are, let's say, related to what I've presented before, more or less the same approach as you can use also for the delineation of EIUs. So you have some predictor variables that are, let's say, describing your processes. So in this case, soil parameters or soil properties, and in the end you can have a look at with this stochastic modeling if they are correlated, so the predictor variables with the target variables, and if you find a good correlation, you can use that then in order to do the spatial prediction of the soil properties for the entire area. So that are some of the procedures we are normally using to get spatially, let's say, meaningful, spatial distributed information about these soils. Yeah, and let's say recently also the proximal sensing techniques are coming up, so easily applicable, for example, in order to get information about the mineral content of your substrates, which is very important in soil erosion modeling, not only in the surface, but also, let's say, on the subsurface areas. Here we have an example of some gullies in Southern Africa. Good. So some outlooks. What do we have to tackle in future? So that is especially, let's say, research questions that are related to climate change. Here we have an image from publication of Jacob in 2013. So on the left-hand side, you have, let's say, the change in annual precipitation. 2071, 2100. So we have, as you see in blue here in the upper parts, Central Europe, Northeastern Europe, we have an increase in summer precipitation up to 30%. Here in Northern Italy, it's more or less remaining the same, and you have some other areas here in the southern parts of the Mediterranean, which has also change in annual precipitation that is negative. If we have a look, that is here, the annual precipitation on left. On the right-hand side, we have the summer precipitation. There you see the percentage change in the summer precipitation here is negative, so that is normally reduced up to 40% here in Portugal, for example, parts of Italy and Greece or Turkey, whereas in the northern parts of Europe, you have an increase in the summer precipitation. However, there are large parts where precipitation is not changing, like here in Eastern Europe. So where you have no change in summer precipitation, or it's even less, but you have an increase in annual precipitation, what does that mean? That means that you have more and more intensive precipitation in the winter months, where normally the soil, especially in the agricultural areas, is not protected by vegetation. So what we can expect in the next decades is an increase in soil erosion due to, let's say, changing precipitation pattern as here forecasted by Jacob, for example, for the representative concentration path weight scenario 8.5. So obviously, according to the scenarios, so you have here on the central part the scenarios that are related to the CO2, let's say CO2 equivalent, and you see, so the doomsday scenario is the LCP 8.5. So let's say middle in between is the RPC 4.5, and then we have a quite nice scenario with the RCP 2.6. But even if we take, let's say, this scenario, RCP 2.6, you see soil erosion increase in percent here globally between 2019 and 2070. And so we have over here in the Northern European area, we can expect, even with this, let's say, RCP scenario 2.6, an increase in soil erosion as published by Borelli et al. So I don't want to get into detail, but you can have a look at, let's say, maybe later on the PDF. But the message is, soil erosion is getting worse with climate change in the next decades, especially also, let's say, here in Central and Northern Europe, as you see in the upper right. Okay, so that is also, let's say, a challenge for us, for our scientists, in order to have a look at, so how can we prepare, let's say, the farmers, for example, or the politicians, in order to, let's say, set up some coping mitigation methods, and therefore you could use then also, let's say, this framework of modeling in order to have a look at what is happening in the future. So as we did here, for example, in Tuscany, southern Tuscany, we did a scenario analysis using the EOU concept, where we changed then, let's say, in the modeling, the different factors like climate, but also socioeconomic drivers were changed in order to have, in the end, sustainable landscape management. And this is a kind then of decision support tool, sustaining farmers or even politicians to, let's say, apply the right measures in order, in the end, to have a sustainable agriculture or sustainable landscape management that is keeping the soils in place and avoiding soil erosion. Good. So then I'm almost at the end of my talk. So just a small summary. So as we have seen, soils are very important. They are, let's say, the base for our life, and let's say the destruction of soils or soil loss is also, let's say, related to a monetary dimension, as we have seen. The problem was that that was not really distributed equally, but there are nations that are more affected by soil erosion. For example, Southern Europe is more affected by erosion than the northern parts of Europe, for example. So then we have also seen in terms of modeling that the soil erosion processes are acting on different scales, and that it is difficult in order to model these processes. Then we need specific models that are respecting the different spatial temporal scales. So anyway, so there are also some solutions to do some integrated modeling, for example, using the response units, where we have areas that are characterizing, let's say, the potential for having a certain erosion process, and that we can use them in order to, let's say, apply different models for different soil erosion type susceptibilities. And these EUs can be delineated quite simply using some stochastic approaches, as showed by the example we have seen from Sicily. And then in the end, we are also able to apply some numerical process models. But however, there we have to be careful with the resolution and quality of the input information, especially soils are often, let's say, treated a little bit in a way that, let's say, you don't have in the end the correct information to do a proper modeling. So normally, so you can be lucky if you have at least, let's say, rudimental information about the soils. So, and I showed also on the end a little bit some research deficits, so especially related to what I said just, regionalization of input data. So routing between the EUs, connectivity approaches. And then I see a very, let's say, large, very large benefit in applying some scenario analysis in order to prepare, let's say, our agricultural areas, the farmers for the future, to have a look at what is happening with climate change, where do I have to be careful in my area, and what kind of measures or coping strategies I can apply in order to keep the soils in place. Good. So what I am very interested in, just to give you also outlook in terms of the focus of my working groups. So in terms of soil erosion assessment, we are working on, let's say, developing our EOU modeling framework, so integrating also other erosion processes into it, like wind erosion, for example. We have just created a plugin for QGIS and ArcGIS for doing gully erosion modeling, the Dimgle for GIS, that is based on the Sidorchuk models. And we are also working quite a lot on the preparation of input data of the models, so applying digital soil mapping approaches and incorporating non-invasive field techniques or remote and proximal sensing techniques. What I would say, it's very challenging and bring a lot of benefit in the modeling procedures. And in the end, global change assessments, I think it's also an area where there's a lot of possibilities, scenario analysis and sustainability analysis, in order to prepare, let's say, politicians and farmers for the future. Good, I guess. That's all. Thank you very much for listening, and don't know if you have questions. I will be happy.
Thank you, Gael, a lot. Very exciting and detailed talk. We can, there is some question in the chat, and also we also have the questions from the audience if there is something. So the questions, what's this picture? Is it Vernatsa?
Yes, that is Vernatsa actually. Where we had very excessive rainfall. I don't remember actually. I think it was 2012. Where we had a rainfall event of roughly 500 millimeters in one day. So we are on the coast of Liguria, Cinque Terre. where you have, especially in the autumn and winter months, you have the cyclones that are coming in, bringing a lot of, let's say, clouds full of water that are then, let's say, blocked by the Apennines, and then you have very intensive rainfall events. And one of these events actually destroyed the Vernazza town and covered, let's say, the historic town with a lot of sediments, and also a couple of people were dying during this event. So let's say here we have, let's say, also combination between, let's say, the classical sheet real erosion process, but then also landslides were activated in this event that lead to the high amount of sediments that were washed then down to the town that is at the outlet of the catchment towards the sea.
Okay, so there is a few more questions, and Nikolai Sinsky, I see the hands.
Yes, thank you. Mikhail, thank you for a very deep and interesting review. I have one question. I have two questions, but I will ask one. You've shown a diagram with models, and there in the beginning of your presentation, and there it was shown that the lithium model was used on the period of applications of this lithium model falls on 2002-2005 period, this very short period. The web model was used for years. So what's your opinion why lithium model is not widely used for, wasn't widely used for sediment modeling, or it's not true?
So as I said, it is always related a little bit to the input data you need for driving these models, right? So, and the more sophisticated models like AGAMS, LISEM, SWOT, where you have to, let's say, set up also the hydrological model first. Then in the end, it's always easier to apply a traditional USLE approach where you have, let's say, the hydrology covered by the R factor, so the rainfall erosivity, and you just need, let's say, less and maybe also less data to drive these models. In the end, let's say, the other models are less used, especially because they are more sophisticated, I guess. So you need more data, and you need also more expertise to drive these models.
But the new data appear with the time goes.
Yeah, so there are a lot of models on the market, but let's say the astonishing thing is, if you have a look at the period 2014-17, still, let's say, even though you have better models, so the most used one is the USLE. So, and that is, let's say, due to the fact that the USLE is less sophisticated, and you get easily results, even not getting deeper into it, and let's say applying, let's say, data you can, let's say, use download from the internet and just apply. So it's much easier to apply these models in respect to the others that have then also a sophisticated hydrological component. So because there you need to know also, and you have to calibrate and validate also the hydrological part of the model that you don't need for USLE, for example.
Understood. Also, my last second question. This method of ERU, the response units, erosion response units, which is very similar to hydrological response units, as you said.
Absolutely.
Erosion response units, are they? Do they appear in the process of modeling? Is this an iterative process, or we can detect it completely before the modeling process?
So actually, you can apply it in two ways. On the one hand, let's say the EAUs, if you derive them with stochastic modeling, is giving you the information where in your landscape you have a high potential for a specific erosion process, right? So you know where you have to apply what kind of model. So in a lot of cases that, let's say, facilitates a lot the application of the more sophisticated models. So for example, if you have, as I've shown, let's say, real inter-real erosion process and you have gully erosion processes, and with your EAU, you know where you have what kind of process. You can limit the application of the sophisticated models to just these areas where you have, let's say, the gully erosion, for example, and use a more simple approach to get information about the these real inter-real erosion processes, for example. Yeah, so that means on the one hand side, you get the spatial distribution of the susceptibilities towards specific erosion processes. On the other hand, if you know where you have a certain, let's say, disposition to a specific erosion process, you can then apply also in these areas, just limited, then a specific model for this erosion process. And as I said before, most of the models tackle just one process. For example, in this image over here, you don't see any model that is tackling, let's say, or marginally tackling gully erosion, for example. Therefore, you need completely different models normally. Yeah. So all these points you see over here is mainly, let's say, addressing real inter-real or sheet erosion process, so aerial erosion.
If modeling is inaccurate, for example, in some areas, we can change this distribution of erosion responsibilities, for example.
Yeah, so that, let's say the approach is a little bit coming from hydrology, where you had, let's say, we have the same approach. Actually,
but they are not equal. But they are not equal. Hydrological responsiveness and erosion responsiveness are not equal in general.
Yeah.
Thank you.
Okay, thank you.
Thanks, Nikolai. And a few more questions. I guess Anatoly is raising a hand. And
yes. Thank you very much, Mikael, for your talk. Actually, one small question. I was really interested in your stochastic modeling results. Actually, I have never heard before about tree-net model, and I'm just wondering, is it possible to get some feature importance from tree-net modeling? So can we, the question is, what is the most important feature predictor according to gradient boosting?
Yeah, let's say more or less it's all the same family. Yeah, so it's classification regression trees, boosted regression trees, and tree-net is a kind of boosted regression tree actually. So you always get also the information about the variable importance by these, let's say, stochastic models. As I said or showed before, in this case, you are also able to identify the most important ones, or at least you can check if what you have modeled is reasonable or not. So if you can explain it and it makes sense, then let's say the probability that your model is correct is quite high. Nevertheless, so you always should check not only one model, but you, so that is my experience, we normally apply different models in order to have a look at which is the best performing model. And so in order to get an information about if the models are robust, they should also, let's say, produce more or less the same results, showing, for example, same variable importances. So if that is not the case, then it's always a little bit difficult. So you have to dig into it a little bit more. But so generally, if you apply different models, you have more or less the same results. Then you can, let's say, deduct also that, let's say, the models are performing quite well, and that the results you get are quite, let's say, robust, and let's say you can apply then, you can trust the models in the end. Yeah. So that means I normally not use just one model, but different models and compare the models. And in the end, maybe you take the one that is performing best in order to get the best regionalization results. To create your maps of the spatial distribution of the ERUs, for example.
Okay, thank you.
So
by the way, there's also a question in chat. Maybe
let's listen for last oral question, then read from the chat, and then we will switch to the next lectures for us required. Somehow shooting time can to be. Victor, you was raising the hand.
Hello.
Okay, no. Yes.
I have a small question. I have lots of them, but the main is, what's about the deposition mode in your model? How it works?
I didn't get it. So can you repeat?
How the deposition step mode was the way of its usage?
Okay, so let's say deposition can be handled in different ways. Normally what we do is, so we apply the ERU concept on pixel base. So that in the end, you apply your model and you model the sediments that are eroded and that are available for being transported away. And then let's say you have to connect these pixel-based, let's say, output you have produced with a connectivity model, with a sediment routing routine. For example, the simplest way is to apply flow accumulation, for example, weighted flow accumulation. That would be the simplest way, but obviously there are also more sophisticated approaches that can in some way take into account also the deposition of the material where you have, let's say, the slope is getting flatter, where you have, let's say, decrease in transport capacity. So let's say models that are taking into account, for example, the slope of the river system and the catchment area, for example, in order to get an idea of the flow volume and the maximum of sediments that can be transported. So there are different approaches you can apply. Also over there, it's always depending a little bit on the information you have. So the more and more precise information you have, the better you can do. Then in the end, also, let's say the sediment transport in your river system, for example. And important is always that these approaches then are in some way also validated. For example, if you have information about sediments that are washed into a reservoir that is on the way, for example, if you have bathymetries or other things that you can use to validate your model, that is very important in order to have a look at if it is working, then your approach. So not only the production of the erosion on the slopes, but also the transport and potentially also deposition on of the material in between. Along the flow path of your drainage system.
Okay, thank you.
Okay, thank you, Mikael. So maybe I will very briefly have a look on the chat. There is a question which was sent by one of the colleagues in the some beginning of the middle of the lecture, and so that's. One is topic related. I think some of the issues were the ends you mentioned already, so maybe the first one is not needed to discuss. As far as was some, it's about satellite data.
Okay. Yeah. So yeah. Actually,
comment.
Actually, satellite data was used, especially in the delineation of the ERUs, because in the end, satellite information, I mean, if you use, for example, Sentinel data, is describing, let's say, the coverage of the soil, so the vegetation, land use. And if you have, let's say, as I have shown before, for example, NDVI, getting information about vegetation cover, and vegetation intensity. That is always useful, let's say, also for the soil erosion modeling. So, for example, to derive C factor in the user-Lee, the cover factor in the user-Lee, you can apply satellite data in order to derive the C factor. But satellite data we also use, for example, in the regionalization of soil information, because, for example, mineral information you can derive with multispectral or hyperspectral data. So if you have, for example, the red infrared information, you can get information about the mineral composition of your surface, which is also giving you a lot of information then in the end concerning soil erosion. So if the soil is more erodible or less erodible, if you have more clay minerals or less, so if your quartz content is higher or not, so that can be also derived with the satellite data. For example, I showed the example in Tanzania where we created the soil map that was done with the rapid eye hyperspectral data, so also very high resolution. So you get around 5 meter scale. So that is quite pretty good, especially if you work on catchments on larger catchment areas. Obviously, so concerning the minerals, you don't. So it's you can just get this information if you don't have vegetation. So. But anyway, for agricultural areas, for example, during the winter periods where you have no crops on, so this is a very sophisticated way to get spatially distributed information. So, and concerning recommending, so there are different sensors, different, let's say, resolutions depending on the research question you have and let's say the budget you have available. So, don't know. Are there other questions, Sergey? Don't know. So,
Sergey, we can't hear you.
I guess the others I more or less I already tackled, I guess, right? So if not, let me know. Yes, here there is one also very interesting part here. Shrinking and swelling of clays. That is really interesting stuff because so that is affecting a lot surface runoff generation processes. So we have this problem, especially in the northern parts of the Apennines, where we have these clay deposits, and you have a lot of active layer clays over there. Cracking plays a very important role in the entire hydrology of the area. So cracks are developing in the summer months, and they are getting up to 2 meters depth. And so if you have the first precipitation events after the summer season, so if you're going towards autumn, so often you have no surface runoff at all because the whole water is, let's say, infiltrating in the cracks. So you have preferential flows towards the lower parts of the soil. And that is connected then in some way also with the generation of landslides, because if the water is getting in the soil on a specific layer, then it's facilitating normally also landslides. So on the one hand side, you don't have erosion. On the other hand, you might have an increase in shallow landslides, for example. So, but it's still a problem. So swelling, shrinking, and cracking soils are still a problem, especially also in hydrology. And to model it, it's really difficult. Another challenge actually for the future.
Okay, thank you very much, Mikhail, for your talk and for your questions.
Thank you very much.
It was really interesting. So I'm looking forward to work with you more and to interact with your work. So thank you very much. And now we are going to our second lecture for today. Dr. Andrey Zhidkin from the Kuchayev Soil Science Institute. Andrey, are you here? Okay.
Yes.
Hello.
Hello.
So I think without further ado, I can give the floor to you. So if you are ready.
Yes.
Thank you. Okay, perfect. We can now see your screen.
Okay. Then I start?
Yes, please.
Okay. I will tell about historical reconstruction and forecast of soil cover degradation based on erosion modeling and field soil survey data. I will try not to talk much, maybe about an hour. The main positions of the lecture are, I will talk about erosion and soil cover degradation. Next, about general issues of soil erosion modeling. Next, about input parameters and assumptions of BOTMCDM. BOTMCDM is the name of the model. Previous speaker told you about it. Unfortunately, I didn't hear the lecture, but I will see it on YouTube. I saw the last picture and what it was interesting. The next, I will talk about verification. Next, historical reconstruction of soil erosion rates. And next is about digital mapping of erosion soil cover patterns. So, erosion and soil cover degradation. I think that everybody knows that soil erosion is a negative process, and the main negative effects are connected with soil degradation and pollution of rivers and other water bodies. And just a second. Today I will talk about connection between soil erosion and degradation of the soil cover. And first of all, I would like to tell about one important thing, that the process of soil degradation is very discrete in space. Now we usually use digital maps, rasters with cell size 20 to 20 meters or 30 to 30 meters and or more. And it is important to keep in mind that in one pixel, we can have principally different soils or degree of degradation. So when we talk about pixel, it's not one soil, it's several soils with different properties. Why is it so? First of all, because of snow melt erosion, which usually forms very discrete soil erosion cover patterns. Rainfall erosion is different. Heavy rain erosion events form wide areas of eroded soils, usually clearly confined to the relief. And in the areas with predominance of rainfall, it is traditionally thought that the shape of the soil cover patterns, of erosion soil cover patterns, is dendritic. Different geomorphological processes forms different shapes of the cover patterns. And this one is classical erosion. Is it so or not? I will talk about it later. Another important question is sediment deposition, which forms reclaimed soils. Our studies shows that in some regions, we can see a rather big share of the reclaimed soils of the area, even on the cropland. And of course, tillage erosion, the main important problem. So, few words about the established practice of mapping of eroded soils in Russia. In Russia, we have a lot of recommendations, but we have only one instruction. It's the government document, and we have to map using this document, using this methodology. Unfortunately, this instruction was written about 50 years ago, and it has some disadvantages. The conceptual methodology is very simple. Simple guys go to the field and dig soils. It is called soil profile truncation method. And then they measure the thickness of soil humus horizons and other morphology properties. And after that, they draw maps. The main problem is related to data interpolation from a point to the surrounding area. For example, here you can see point here, here, and here. And I don't know why the boundary of different soils is like these shapes. It is here. It is very, very subjective. So the problem of state methodology is that we use factors and soil properties. But soil erosion process that is really good studied now almost doesn't used. Soil cover mapping is carried out on the basis of expert opinion, usually without taking into account the process of soil erosion. We decided to try, what if we will use modeling? What if we will include modeling in this chain, factors, process, properties, and map the degree of soil cover degradation? This is some of our results. I will show the methodology and the results in different regions of Russia later. Because first of all, we have to talk about soil erosion modeling. Because this is young school, I decided to include some pictures, just a few words about soil erosion modeling to understand the main ideas. First of all, as unfortunately I didn't listen the last speaker. Maybe he talked about it, but I want to say that modeling has a long history. It started about 30 years in last century, and in the 60th it was a revolution which was made by Wishmeyer-Smith. They made very good model, which some scientists use until now. And the conceptual idea of this model is to use factors, rainfall erosivity, soil erodibility, topographic slope and length, crop erosivity, and erosion control factors. I think that most of you know it. And the coefficients were empirical. It were taken from a lot of about thousands experiments on stock stations. Important to note that traditional stock station length is 22 meters. It is very important when I will talk about it, when I will talk about using of digital elevation models and the cell size of digital elevation models, which should be close to this distance, to this length, to about 20 meters. Okay, number of publication of modeling of soil erosion is rather big. It's, I think, about close to 1,000 in a year right now, but I will talk, we have numerous works of verification. And special problem, it's how to select model, because we have a lot of different models. In some reviews, we can see even 82 models. And it's not only international, except international models. We have some regional models. For example, Russian and USSR models are in Russian language and they didn't translate it. They were not translated into English, unfortunately. So maybe, I think in the world we have more than 100 models. And how to select model? First of all, it should be model algorithm, the time window, the study scale, and integration into computer programs and online services. Model algorithm, you should know what to simulate. It should be a rainfall water runoff or snow melt water runoff, and the big difference between empirical models and physically based models. This is just my subjective opinion, that I think that empirical models easy to use. They have less and easy input parameters. Some of them have different scale, can be used in different scale. But if you plan anti-erosion measures in detail scale, I think it's better to use physically based models. So you can look this paper and read about it. According to Pandey, what Amsterdam and web model is universal for different scales, but some people think, some scientists think that it can be used in detail and medium scale. So we use what Amsterdam program in our studies. And integration into computer progress and online services, it differs for different models. If you, for example, this is the example model Russell 2. If you study United States of America, you can use it online for any part of the United States. But unfortunately, we don't have like these models and online services or modeling for Russia. So what Amsterdam, input parameters and assumptions. The algorithm of this model is based on Russell, so it's almost the same as I showed before. Few words, just few words about input parameters. LS factor. I think that erosion modeling now have renaissance. It has last 10 years we have big interest to the erosion modeling. First of all, because of development of digital elevation models, DEMS. And now we can have, everybody can for free take, for example, SRTM or ALICE and calculate erosion in a rather detailed scale. But important to note that there are different equations of calculating LS factor, and you should understand what you do what equation do you use, because you can have different result if you use different equation. Unfortunately, in some papers, there is no information about what the model, digital elevation model that was used, about the cell size that was used, about the equation that was used for calculating LS factor. And I want to show just one example. Unfortunately, I know only few works, and I think this demonstrates rather clearly. I'm sorry for Russian language. In one small watershed, we calculated soil erosion using different digital elevation models, and we calculated erosion losses from 400 from the cropland tons, 400 tons to 1,200. Is 3 times difference. So it is very important what model do you use, what digital elevation model do you use, and also important the cell size. We found that for example, East European, Russian, Middle Russian upland, we can use ALAS, SRTM, and UAV digital elevation models. They have rather good agreement. But important to note that the cell size different. We found interesting thing that the correlation between the area of interslope accumulation and dam size cell. So when you use very detailed dam, you can have very small interslope accumulation, and in other side it works the same. When you have big dam cell size, you have large area of interslope accumulation. We used what Amsterdam. That's not good, of course. So I recommend to use the cell size that is recommended in the instructions for the models. For example, for Amsterdam and for other ASL and Russell based models, it should be 20 to 20 meters. Of course, using different dams, we can see different special structures, quality of special structures. I will not talk much about rainfall resivity. We use this work, and I know that for Russia, this work made very good scientists, this part of work, and our works on verification of soil erosion models shows that it really works. But I will talk later about reconstruction of soil erosion rates of soil erosion. If you reconstruct something, of course you have to reconstruct changes in rain erosivity factor also. And just one word about crop erosivity factor. It's very different for different croplands, and this factor is the most uncertain when you reconstruct something. And when we calculate soil erosion, we usually calculate different scenarios, minimum and maximum, because we can't reconstruct crop erosivity factor for 100 years, for 200 years. It's just impossible. This information is absent. Verification. Important to note that there is no difference between erosion modeling results and expert opinion if you didn't validate your calculations. Unfortunately, I have to reject some papers, about 2-3 papers in a year, where people try from different regions of the world, try just calculate soil erosion. this is not the result of the work. The calculation is just calculation. It's the technical procedure. It becomes important. It becomes scientific when it is verified. But unfortunately, we have just not so much works about verification of soil erosion models. It's about, for what Amsterdam, 20, 30 papers, works, I know. Comparing to the all works about using soil erosion modeling, about 100 in a year or 1,000 in a year, it's very small part of the papers. I know that most of people who listen me is from Russia, so I'll just give some examples from our work in Russia. We did it in two or three, in maybe 5 objects. One of it is presented on the picture. You can see it's small watershed, and we compared it calculations with soil morphology method, with radiocesium also method, and with magnetic tracer method, and usually we have rather good correlation, good result of soil erosion modeling when we use detailed input parameters. And just an example, it's about verification and about reconstruction. Another small catchment, and the interesting thing that in the middle of the 80th years, here changed the boundary of the cropland and became higher, about 40-50 meters in different differs. So we studied it 10 years, and we studied it in very, very, very much detail by different methods. And then we compared it. So if we take permanently plowing part of the catchment, we can see almost no difference between modeling and radiocesium assessments, modeling and soil profile truncation method. But we have very much difference in the non-unplowed parts of the catchment. It is about, this story is about the transport, sediment transport in the bottom of the dry valley. And I think this block of modeling for what Amsterdam should be calibrated for Russian coefficients of transport capacity, because we found that it was much higher. The accumulation is much higher than shows by field methods. You see almost 1,000 tons accumulated according to modeling, and according to field methods in the bottom of the dry valley is accumulated about 250 and 160 tons. It is much less than 1,000 tons. And interesting thing that we found that I want to talk to you, to tell to you, it's that the reduction of arable land by only 5%, but in the lowest parts of the slopes, made that soil loss was reduced by almost 30%. This is very important. So it can be one of the important anti-erosion measures, I think. So now we work a lot about anti-erosion measures, and one of it's changing its territorial planning, its changes in the location of cropland boundaries. Another work we just published about reconstruction. I think this is interesting, maybe interesting for you. We reconstructed in Moscow region soil erosion to 200 for the period 250 years. We reconstructed the cropland boundaries by historical maps and satellite images for this period. We reconstructed, it was very big work, we reconstructed crop rotations for these periods, and we reconstructed climate. All calculations were verified by magnetic tracer method. And now it's like movie, you can watch, you can look how it changed. You can see on the picture that it's very different in this region. The croplands boundary were very different, I can repeat it. And soil erosion was very different. You can see it. So if we look at one picture, we can see a clear trend of reducing of soil erosion rates and volume of soil erosion losses for the period 250 years. But interesting thing that have some peaks, some maximum after the abolition of serfdom in the middle of the 19th century, and it was rebuilding of agriculture after the Second World War, the next maximum. But the old trend is the reducing of the area of the cropland and the erosion rates in this region. And the interesting thing that in this region, the most degraded soil cover is connected to not to the length of the slopes, not to the slope degree, not to the exposure, so on. It just connected to the duration of plowing, which is connected to the location nearby the villages, cities, and so on. So the most degraded soil cover are near the villages because of plowing or duration of plowing. And the main part of my lecture, it's not, I think I will talk about 10, 15, maybe 15 minutes more. It's a digital mapping of erosion soil cover. I told you that we decided what will be if we will use modeling. We will try to use modeling in mapping of soil cover degradation. The idea of I have some technical problems, but that's okay. I found the methodology of these calculations is connected to find the relationship between the rates of soil erosion calculated by the model and the share of soils with different degrees of degradation. So if the rates is 0, you have 100% of non-eroded soils. When the rates increase, the shear of non-eroded soils decrease, and when it increases, the shear of slightly eroded and moderate eroded soils decrease by their personal equations. And then it's just a simple technical procedure. If you use raster of soil erosion rates, you can just build these maps with the shear of soils in the pixel. And after that, you can just add one raster to another, and you have information in each pixel, the information about the shear of soils with different degrees of degradation. So just for example, the study object, we worked on it this year. We made field studies. We studied the degradation of the soil cover in each point. Then we calculated the rates of soil erosion accumulation. And then we made the map with the shear of different degree of soil cover patterns, degree of degradation. So here you can see these maps that were built for different regions of European part of Russia. And here you can see that the structure of degradation is very, very different. I want to note that the scale is the same for all the pictures. And you can see that, for example, in Tambov region, we can have very, very small areas of eroded soils. And it's very small because, first of all, the rates of soil erosion is not high. And the second, that soil profiles, soil humus horizons are rather big, about 70, 80 centimeters. So it needs a lot of time for degradation. And in Orel region, for example, we can see very big areas of eroded soils because of rather high rates of soil erosion. At this study site, it was more than 10 tons per hectare per year for the site in the middle. And the soils are not big, and they have humus horizons about 40, 45 centimeters. What is the shape of erosion soil cover patterns? Usually it is thought that, as I told above, that it is dendron shape. And it is so, but in some regions. For example, this is the south part of the Middle Russian upland. It's Kursk and Belgrade regions, where cropland almost didn't change about last 200 years. And we can see that the shape of soil cover erosion soil cover patterns, repeat the relief, and the size of the areas of eroded soils depends on the degree of the dissection of the relief. High dissection, we have rather big areas of eroded soils. Low dissection, we have small areas. Another situation, it's like focal erosion. You can see in Tambov region, I told about it before, and in Bashkortostan region, it's Cis-Ural region, because the important role of erosion is not only mesorelief, but also microrelief. And the shape of eroded soil cover patterns depends on the microrelief very much here. And the site I've told about before, the Moscow region, where we found that the shape of the soil erosion cover patterns depends not so much on the relief as on the agricultural history, and eroded soils are located nearby villages and cities. Few words about comparison of different methods. If we have tree-like, dendro-like shapes and simple agricultural history with almost no changes in cropland area and location of cropland, changes in location of cropland boundaries, we have almost no difference between digital method and traditional visual expert method. You can see it's almost the same. In some, you can see here, the relief is not so much dissected on the northern part than in the south part. And the visual expert method gave it was the area of eroded soils was a little bit underestimated. But anyway, we can see almost the same situation. And principally another situation we can see in Cis-Ural region where discrepancy in the area of eroded soils was 26%. Because I don't know how, but these experts draw these maps not very good, because the relief is very difficult and the micro-relief should be taken into account, and this is the problem. So that's all. Just I wanted to tell a few words about the method that I showed. We work on it. It's not finished. We have a lot of assumptions using this method. But anyway, I think that I showed you that degradation, and this method shows that degradation of the soil cover, erosion soil cover patterns comes very different in different regions. And we should take this into account. Thank you for your attention.
Dear Andrey, thank you very much for the lecture. So, is there any questions? I can see a raised hand from... Nikolai, yes, please.
Oh, yeah, thank you. I was very curious about this result, historical reconstruction, that after the removal of serfdom, there is a slight peak of erosion. Do you think it's due to the redistribution of fields after this date, after this year's removal? Thank you.
Well, some technical problems. I couldn't hear the question good.
About the removal of serfdom and slight peak of erosion after it. Do you think that it is due to the redistribution of
I'm sorry, Nikolai, I need to interrupt you. Unfortunately, we can't actually hear you. Can you please write a question in chat?
Okay, yeah.
Yeah, some problems with microphone, I think.
Mikhail, please.
So I just have to find the microphone. So thank you very much, Andrey, for this very interesting talk. So I liked it very much. So I was really astonished about one slide you showed at the so in the middle part of your presentation, where you have the area where the amount of agricultural area was always decreasing. So that is really astonishing because let's say it seems that in 1797 almost the whole area is covered by agriculture, and then so in our days now it's just marginally let's say used by agriculture. So what is actually the reason for that? Because productivity is getting up, or people are doing other stuff, or what?
The soils, soils in this region are not. It is the agriculture is not effective here. It's not much profit. So people lived here before. In the north part of Russia, people lived about. They started agriculture about 700 years ago. And it's like it's history, but after that they moved to the south, and less and less areas are under arable area here. And now we have just all the territory nearby Moscow is under the summer houses, and nobody wants to make agriculture here. That's the reason.
So, if I can, another question, if I'm allowed to, don't know.
Yes, of course.
You showed also that, let's say, the soil erosion intensity is in some way linked to the plowing activity. So that was also very interesting because that is reflecting more or less what we have also here in Northern Europe. So where that I showed also in my presentation that tillage erosion is very important and has to be really taken into account because it's really changing the landscape completely. So especially so if applied over let's say roughly 200 years more or less, right? So.
Yes, I'm completely agree with you. And now when we make works for the verification of soil erosion modeling, we calculate tillage erosion by what Amsterdam, and we have much better results of verification when we use this block of calculation.
So,
tillage erosion, yes.
So that's reflecting what we have also, let's say, in northeastern parts of Germany. It seems that tillage erosion is the most important one over there. So that was, let's say, up to 10 years ago, completely neglected. Yeah, but very important, especially in the agricultural areas, actually. Yeah, thank you very much.
Thank you.
Actually, Andrey, can you see in chat that Nikolai wrote his question down?
Just a second. Just a second. Do they think the slight peak of erosion after removal? Yes. It's not. It's just. I will say it in another case. It's not geographical distribution. The area of the cropland became bigger because after the removal of self-dome, the rather big territories gave to the ordinary people, and they started to make agriculture almost on large more territory. Sorry for my English. I had no practice for the last months and forgot everything. But maybe you understood me, yes? But the cropland area became much bigger after the removal of the self-dome. Yes. Okay. Thank you.
Okay. Thank you very much. Is there any more questions? Well, actually, I have one. Sorry.
Yes, I have a question.
Yes, please.
Can the soil erosion modeling be applied to the erosion of riverbanks or islands?
I don't know. I am not a hydrologist, and we didn't use it for. I think that you should use special hydrology models for this task. Usually, you can read about each model and the assumptions and the borders you can use, the tasks you can use this model. I'm sure that what Amsterdam is not used in to assess the hydrological processes, unfortunately.
Okay, thank you.
Thank you. Anybody else want to ask a question? Well, then maybe I can finally ask a question. So, Andrey, what can you please go to the slide with the relationship between cell resolution and soil loss? It was in the beginning. Well, actually,
this.
I have not. Yes, this one. I didn't read your paper, but maybe can you a bit comment on this slide, because your results are mirroring, not mirroring, are controversial to the results of paper of 2005 by Simon Wu, who they showed that actually soil loss is declining with the increasing of cell resolution. So the higher cell resolution of the digital elevation model, the lower is the model soil loss. And you have another relationship.
Thank you. This relationship is not about soil erosion. It is about intraslope accumulation, sediment accumulation.
And the bar plot on the left side?
It's UAV 1 meter, UAV 5 meters, UAV 20 meters, and ALAS SRTM 23 meters SRTM. You can see it. And
okay.
This is topo cards. This is, I'm sorry for Russian, but I think you understand it.
Yes.
This is the top dams that were built on the topo cards. Interesting thing that it was a little bit higher. But we used almost the same cell size. You know, if oh, you told maybe about this.
Yes. So
this part.
Yeah,
and maybe I don't know for sure, but these pictures here you can see the UAV with different resolution, and I think that what Amsterdam uses 20 meters, and I think that when you use very small cell size, what Amsterdam starts to calculate micro relief like mesorelief. So I think that in these calculations, you can see it, it's very small, but you can see it, that the erosion processes doesn't comes to the lower parts. It stops in the middle of the slopes because model thinks that it is enough and it should be stopped here. So this is just an example how not to use model. but I don't but I don't know the real reason of this. Just my ideas.
Okay. So and just one comment about the bar plot on the left side in the lower part of the slide. On the y-axis, is that soil losses? So it is like the Russell part of the WOT-Amsterdam model, or is it a WOT-Amsterdam result?
It's the Russell part of WOT-Amsterdam result.
I mean, okay, the initial WOT-Amsterdam equation just uses the Russell model in the beginning, so just to calculate the soil losses, and then it is applies transport capacity approach to recalculate it to the actual transport of the soil particles. So the question is this soil losses, or it is like final WOT-Amsterdam?
Oh, you ask, is it gross erosion or net erosion?
Yes. Yeah. Okay.
Okay. Unfortunately, I don't remember, but okay. I think, but I will just. I don't remember for sure. You have to look.
Okay,
for...
I will check it in the paper. Okay, thank you.
Okay, I just will switch on to the discussion a little bit. I was get some problem with the microphones on the between the Mikhail lecture and you, Andrey. Thanks for the lecture. So if there is some, and also thanks for Mikhail. So I see that you are still there. So also thanks for the lecture, because I was not able to some final words at the end. Andrey, very simple questions. We are coming to the end. What's the background map on in your room?
Oh,
this is yes.
In my office. This is the map of academic Kashtanov and Chishov. This is the map of soil erosion of the European part of Russia and other nearby countries. And this is very important map. It was 42 organizations made this map in the beginning of the 90th years of the last century. Soil Science Institute made this work, and Moscow State University, Institute of Geography, and other organizations all made this work. They use information about soil cover in each agriculture farm that were studied in very detail in 17th, 80th years in the USSR, and this is the really big work made.
Okay, nice. So
thank you.
Looked like a big, but just I was interested if you are on the top, if you put the background to the topic related to the topic of your talk. Nice. Okay, so also can be good to confirm that we can in some future arrange maybe more like a seminar also, both if Mikhail will be able to do this and you, Andrey. So it's very good possible developments of the lecturing. So at some moment. Okay, there was also some questions in chat if you looked at that as well. It's more like comments, I guess.
I think that's comments.
Yes, okay.
I want to thank the organizers. Thank you very much for this sorry for my English, but I'm very glad to be here and to talk. with you and to present these results and partly our results. Thank you very much.
Very fascinating soil erosion Saturday.
Yes.
And we will be back both to Mikhail, to you, and to you, Andrey, after we finish this lecture series. We will be in touch as far as there will be also thanks from our international associations who arranged this event for you. Yes. So if we then finish this day, so all the if your lectures also, Andrey, if your lectures are available, will be recorded version of your lecture will be also available in YouTube if it's okay with you. So then we keep it in the YouTube channel of the seminar, so the people can later proceed. Great. Toля.
As just a general question from our participants, is it possible for you both, Andrey and Mikhail, to share the slides of your presentations in PDF so we can disseminate them inside our participants?
Yeah, sure. Maybe I will prepare in the next couple of days. So because from tomorrow on I'm traveling, so maybe let's say end of next week. I can prepare.
Thank you very much. So,
yeah.
Thank you.
Great. So have a good weekend. Thank you for joining us on the weekend time, but it's more relevant for the young scientists, especially PhD students and students who attend this to watch during the lectures in normal way. Okay, then we finish this the series. There will be Monday with the lecture of Paulo Porta and Anatoly, and on Tuesday there will be a lecture from Professor Sadeghi from Iran, and this will be the last day which we plan for this year. And hopefully this event is the third year, Mikhail, it's the third year of these lectures, so it's already like coming to be something like a yearly basis network.
Cool. Thank you very much for the invitation and being with you this afternoon. And have a nice weekend all. Eh?
Yes.
Thank
okay.
You.
Goodbye, all participants. Goodbye, dear lecturers.
Bye.
Bye-bye.
Goodbye.